Coq is the tool we will study in these lectures and in Software Foundations. Let me start by acknowledging that the name Coq is a problem for American English speakers. It is a homophone for a vulgar word. That leads to confusion, if not embarrassment, in talking about it, especially with anyone who has not encountered the name before. The name has particularly led to women being discouraged or harassed. That is unacceptable, and it has no place in the class that I teach in this material or in the comments in these videos. As it turns out, the name was cleverly chosen by the French creators of this tool. In French, coq means rooster, which is an official national symbol of France. It's also a prefix of the last name of one of the main creators of the framework, Thierry Coquin. And it is yet again a homophone for the initial letters of the Calculus of Constructions, COC, which is one of the primary theoretical bases for the framework. More on that in just a minute. So there were 3 good reasons for choosing that name. Currently, there is a process underway to identify a new name for this framework. But for now, we have the current name Coq. And so when talking with outsiders, I often rush through something like the following. The Coq theorem prover, that's COQ, meaning rooster in French, and France is where it was created. So, with that out of the way, the history of Coq from the 1980s to circa 2000 can be found in the Coq Art book. Google that, you'll find it. It also won, more recently, the 2013 ACM Software System Award. You can find videos about that as well. What follows will be my highly selective summary, mostly from the Coq Art book. So the difficulties encountered in the first part of the 20th century with formalizing the foundation of mathematics, including some of the impossibility results I mentioned a couple of videos ago, led to the invention of type theory, which intended to improve upon set theory as a foundation for mathematics. A Swedish logician, Per Martin Löf, invented a type theory in the 1980s that was highly influential, not just as a foundation for mathematics, but also of functional programming. At my own institution, Cornell, computer scientist Bob Constable, my colleague, built upon that theory to create a system called New Perl. New Perl would make it possible to extract verified programs from their proof of correctness. In France, at Henriet Rocancourt in the 1980s, Gérard Houet and Thierry Coquin likewise invented their own type theory, dubbed the Calculus of Constructions. More on that as well later. Building proofs in such type theories is challenging, though, for the human prover, leading to a need for assistance from the computer. So Coquin, and later his colleague Christine Moring, implemented automation with tactics to help find proofs. That was the birth of the Coq system. The underlying implementation language was a predecessor of OCaml, and today Coq is implemented in OCaml. Around 1990, the underlying formalism was extended to the calculus of inductive constructions, which was better suited to reasoning about data structures. In the early 1990s, one of Bob Constable's PhD students, Chet Murthy, went from Cornell and joined the Coq team in France, helped implement some of the pieces of the Coq system as it is today. By the end of 2003, Coq version 8.0 had been released, and that was the last change, at least so far, in the major version number. Almost 20 years later, based on half a century or more of research in formal methods, the key ideas remain stable. Coq enables defining commutable functions and logical predicates, stating mathematical theorems and software specifications, interactively developing formal proofs of theorems, machine checking those proofs, and extracting verified programs from that to OCaml, as well as other languages like Haskell and Scheme. Here's the general principle on which a proof assistant works. I owe this figure to the paper QED at Large by Talia Ringer et al. There's a proof assistant and a user interacting with that proof assistant. The goal at the end of the day is to produce a proof. To do so, the user uses tactics to interact with the proof assistant. Those tactics cause the proof assistant to produce proofs, or at least parts of proofs. The parts that it can't produce get represented as sub-goals that are then sent back to the user. The user then has to help the proof assistant complete those sub-goals. So in this model, the user and the proof assistant are cooperating together to construct the proof. Now, after all of these pieces of proof have been assembled into a final proof of the entire theorem to be proved, a proof checker that is part of the proof assistant can then run to validate that indeed that is a good proof, that there are no gaps in it, that there are no errors in it. I think there are several benefits to studying software foundations and this kind of proof assistant technology. First, you can learn to formulate functions and predicates in a type theory, which is essentially programming in a superpowered functional programming language, and that's a lot of fun. You can learn to state formal theorems and make formal software specifications, which requires making rough natural language concepts that you might express in English or whatever your native language is, very precisely in logic. That's a wonderful skill to develop. You can also learn to prove theorems in a completely formal way, which means coming to an understanding of what constitutes a formal proof, as well as how to guide a mechanized proof assistant toward completing the low-level details of that proof, while being smart as a human in doing that guidance. You can also learn to understand proof checking as type checking. This is a deep result. We won't get too far into it in Software Foundations, but it involves learning about the deep connection between proofs and programs. That connection is known by many names, including propositions as types, the Curry-Howard isomorphism or correspondence, or the BHK interpretation, BHK there is standing for Brouwer, Heiting, and Kolmogorov. Whatever you know it as, that connection between proofs and programs is at the heart of the modern connection between the fields of computer science and logic. So it's a really wonderful thing to understand and make that connection between these two areas of scientific inquiry. Now, I think of Coq expertise as a side effect, as a beneficial side effect from all of these other wonderful things that you can learn. Nonetheless, it may be exactly the side effect that you're here for. So learning Coq can be good too. Whether or not you ever extract a verified program after studying this material is, to me, maybe not the point. By studying formal verification, you will have sharpened your skills at reasoning about programs no matter what. Nonetheless, there are some great projects out in the world that are producing verified code. So let's take a brief look at a few of those next.